In this video, I'm going to explain about important factors of fluid in motion. Let's start with answering why does a fluid flows? Fluid flows because of special molecular property. Fluid molecules are not rigidly attached to one another as in solids. So when a force is applied, it deforms continually. When a force is applied on solid, it deforms, but it doesn't deforms continually. So this continuous deformation in fluids is called flow. So why do we need to understand the fluid flow? What is the importance? So we need to understand the impact of fluid in motion on our structures and design them accordingly. For example, when we design a water supply pipe from a river intake to treatment plants, we need to decide the alignment of a pipeline, right? Alignment of that pipeline. So that depends on understanding of the fluid in action. We should also answer how big should be the pipe. We are also interested on how strong the pipe wall should be so that we can transport water without getting it bursted. So to answer these kind of questions, we need to understand what are the factors that affect the fluid flow and what are the factors that are in action. We know moving fluid is very complex, and that's why it is difficult to represent them mathematically, because factors such as turbulence, viscosity, density, that defines how much flow can occur through a particular section. That also defines the impacts of the fluid on pipe walls. Similarly, how much energy will be lost during the flow process and so on. So let's talk about these key factors. So the key factors are the turbulence, viscosity, compressibility, density, and so on. Now let's look at the first factor, which is turbulence. Turbulence is basically the measure of mixing of fluid particles when they are in motion. So let's see a figure here. This is a smoke from a cigarette, and up to certain height we see a kind of streamline of the flow of the smoke, and after certain height it seems to be a random flow. So this area, this flow is called turbulent flow, and the flow which seems to be streamlined is called a laminar flow. So laminar flow is basically a flow on which the particles move in a streamline. They follow a same path and have same velocity. So that's called the laminar flow. Whereas in turbulent flow, all particles follow different and random paths and have different velocities. So how we define turbulent and laminar flows? So we use Reynolds number to define it. Reynolds number is a criteria to define if a flow is laminar or turbulent. The values are different for pipe and open channel flows. For a pipe flow, a value greater than 4000 is turbulent and less than 2000 is laminar. Similarly, for an open channel, a value more than 2000 is turbulent. Now let's look at viscosity. To understand viscosity, let's look at a figure here. The bottom plate is fixed and top plate can be moved when we apply force, and in between these plates there is a fluid, let's say water. Now apply some force P on the top plate. What happens? The plate starts to move at a constant speed of u, right? So the plate starts to move. Now, because when a force P is applied to the top plate on a liquid, it moves with a constant speed u, and it generates the shear stress, right? So it generates because when you apply the force, it generates the shear stress here. Because the liquid cannot resist the shear stress, then it has to deform continuously. So that means when you apply the force, the liquid has to move, right? However, at the bottom, the plate is fixed, which means the bottom layer of the liquid does not move at all. So this creates the velocity gradient. At the top, the velocity is u, and at the very bottom, the velocity is 0. For an ideal fluid, the velocity gradient is linear. So du over dy equals to top velocity divided by the depth. For many liquids, the shear stress is directly proportional to the rate of shearing strength. This tau shear stress equals to mu, which is a constant and is also called the dynamic viscosity times the velocity gradient. And this dynamic viscosity is a property of a fluid and it depends on temperature. So this dynamic viscosity is a measure of the ability of one layer of fluid to move across another layer. Okay, and the fluid obeying this relationship that the shear stress is um, directly proportional to the velocity gradient is called those fluids are called Newtonian fluids, and the fluids that do not obey this rule is called non-Newtonian fluids. Now let's talk about compressibility. In hydraulics, we assume water is incompressible, but if you want to measure the compressibility, we use the bulk modulus as the parameter. Now let's talk about an ideal fluid. An ideal fluid is one that does not have viscosity and is incompressible. So in reality, there is no ideal fluid in nature. Then why we need this? Because we need to simplify the fluid problems. We know the fluid in motion are very complex in nature. If you want to define them mathematically, the equations becomes very complex. So we want to simplify the mathematical equations, and that's why we assume and derive the mathematical equations for an ideal fluid, and then we extend it to all the real fluids by adding some coefficients. So there are other ways of classifying the flows. The first one is steady and unsteady flow. Steady flow is the one in which the flow characteristics like velocity, pressure, or fluid characteristics like density at one particular point does not change with respect to time. So it remains the same whenever you go and measure. And just the opposite to that, the values change at a point when it is measured at different times, then the flow is called unsteady flow. Another way of classification is uniform and non-uniform flow. Uniform flow is the one in which the condition of flows remains constant from section to section. So if you measure at multiple sections, the condition of flow remains the same. In non-uniform flow, the conditions of flow does not remain constant from one section to another. What kind of mass do we need to define fluid in motion? We know fluid flow is a very complex phenomenon. There are several equations with different levels of complexities to represent flow and its other physical quantities. However, there are three fundamental important equations which are sufficient to solve most of the fluid flow problems. And these equations are continuity equation, energy equation, and momentum equation. Obviously, there are some additional equations. However, These three fundamental equations are sufficient to solve most of the fluid flow problems.